Okay, everybody. I thought that it would be good to see at least one more example of an optimization problem. Um, Given that I guess every scenario could be a little bit different with this type of problem, it'd be good to show you one that's completely different than any that I've included in the videos so far. So, okay, now I haven't written out the question. I just have this scenario right here that I want you to think about. And then about that scenario, I'll ask you to consider a few follow-up questions, and then we'll do the math to arrive at the answers, okay? So imagine a scenario like this. There's an object right here at that point, okay? That point is, on the xy plane, it's 4 for x and 7 for y. And suppose that the object that's there starts moving directly to the left at 2 units per second. So what's that mean? Well, it's initially at 4, and then 1 second later, it's at 2, and then it's at 0, and then it's at -2, okay? So even though that, as I say this, you might not be sure how the math's going to work out with that, you can at least plot where the object is going to be 1 second at a time, given that it moves left 2 units per second, okay? And then say at the same time, there's another object that starts at the origin, 0 for x, 0 for y, and it moves up at 1 unit per second. Now again, you might not be sure how the math works out yet, but if it moves up at 1 unit per second, it starts here at 0, and then it goes to 1, and then 2, and then 3, 1 second at a time, all right? Now, I didn't consider like fractional seconds. It's where's this object 3.7 seconds after it starts moving? Well, okay, I mean, it's 2 units per second, so we could divide that up and figure out where it is 3.7 seconds later. But I'm not worried about that now. All I want you to see for now is that the objects are moving like this, sort of like this, okay? Sort of like this. Now, so with that scenario in mind, let's think of the questions, okay? When will the objects be the closest? We'll see that word closest. That's what makes this an optimization problem, okay? As if like as they move, they'll approach each other and perhaps get to these points where they're as close as they're going to get, and then they move forever away from each other, further apart from there, okay? So when will they be the closest? Where will they each be at that time? And how far apart will they be? Now, really like 3 identical questions, really. Each of these will have a different answer, but they all relate to the same thing in that at some moment the objects are as close as they're going to be. Okay, when will that happen? Where will they be? And how far apart will they be? Now, hopefully you can, again, maybe you don't know how the math's going to work out with this yet, but you can imagine that as they move along these paths as described, that they will be, at some moment as close as they're going to get, and then just drift further apart as they continue to move. Okay, so that's what we're after. Now, so time for the math. How do we do this? Well, so I guess, as you would think, you need a formula. We need a function. In calculus, we learn to have functions and then find their derivatives and do different things with the derivative, okay? One thing that the derivative of a function can do is solve an optimization problem. So what's the function? Is there some kind of formula that describes what's happening here? Like, for example, is there some kind of formula that tracks the distance between these two objects moment by moment? All right. Well, so let's do this. First, can I even tell you where this object is moment by moment? So I'll propose an answer for you. I think something that would track the movement of this object is this, 4 minus 2t for x, 7 for y. You give me a time, this formula will tell me where the object is. Now, is that consistent with this statement that it starts moving left at 2 units per second? Well, okay, think of it like this. when t, so say t is time in seconds, when t is 0, where does this put the object? 4 and 7. Well, that is where it starts, right? And say when t is equal to 1 second, where does this formula put the object? Well, what's 4 minus 2? So that's 2 and 7. Would that be right? Well, that's 2 units left, okay? And then you get the idea, right? When t is 2, where does this put the object? 0 and 7. 2 more units to the left. So this will do it, all right? 4 is the original starting point for the x-coordinate minus 2 units per second times t, okay? This will track the location and the movement of this object as it moves left 2 units per second from this initial point. 4 minus 2t, comma 7, all right? X and y coordinates. In the same way, we can do something like that with this one. It will be 0 in t, right? I mean, does that make sense? Its x-coordinate will always be 0 as it moves up, and it moves up at 1 unit per second, so the y-coordinate will just be t, because when t is equal to 1, the y-coordinate will be 1, and when t is equal to 2, the y-coordinate will be 2, and so on and so forth. Okay, so these have a similar principle in their derivation. Now, I want to find, like, what's the minimum distance? Do you see the word closest? So it's like, okay, from here I'm thinking, is there some function that will measure the distance as these things move? Here, these formulas give me the location as they move. But is there a formula that gives me the distance? Okay. Well, there is something called the distance formula that we've learned about on the xy plane. It gives the distance between 2 points on the xy plane. You remember the distance formula? Well, the way that works is that, say we've got, just for whatever graph, whatever the situation is, there's this point here, let's call it x1, y1, and then some point somewhere else that we'll call x2, y2. And suppose we want to know this straight line shortest distance between the points. That's what we mean by distance. Then that's found by this distance formula. You subtract the x-coordinates. We do x2 minus x1. We square. And then we do subtract the y-coordinates, y2 minus y1. And then we square. And then we take the square root of that. But I'll write that as the 1/2 power upon that whole thing. That's the distance formula. Now you can subtract the x-coordinates in whatever order you want and the y-coordinates in whatever order you want, because when you square, it's all going to work out. 5 minus 3, what's that? 2 squared is 4. 3 minus 5, what's that? -2 squared, still 4. It doesn't matter the order you subtract. It definitely doesn't matter the order you add. So I'll just give you the distance formula that way, and I won't elaborate any more about it. Okay? All right, now, so from here, though, if this right here tracks the location of this object moment by moment, and if this here tracks the location of this one moment by moment, then let's just apply the distance formula to these points, and then that will be a function that tracks the distance. Can you think of what that would be? There it is, right? So think of how I did that. I took this x-coordinate minus that one. All right, well, that's 4 minus 2t, take away 0. That's 4 minus 2t squared plus 7 minus t, all right? These y-coordinates, 7 minus t squared, and I add them and take the square root. So there it is, all right? So to find when that distance is a minimum, or when they're the closest, I just need this. I need to take this function right here and figure out what it takes to make the derivative d prime equal to 0, this distance being a function of time. Okay? All right, so let me go on the next page and show you the math for that. First of all, I did a little math to simplify that formula. So where's 5t squared minus 30t plus 65 come from? Well, that's what you'll get if you multiply all this out and combine the like terms, okay? And I just thought it would be better to handle it that way, so that's what I did. So you'll get d is equal to 5t squared minus 30t plus 65 to the 1/2 power. And there's that function that gives the distance between the object at any time. Okay, and I want to find the minimum of it. I do that by finding the derivative and setting it equal to 0. Okay, so we started with this, right? And then there's d prime. And I hope you recognize the rule that's at work here, but it's the chain rule. Okay. And let me do something to simplify this a little bit, like that negative 1/2 power can put this expression down there, and I've got a 2 there, and I've got a 10t minus 30 on top. All right. I could take this a little bit further. I could cancel the 2 into the 10 and the 30, but I'll just go ahead and leave it because that's not going to really make much of a difference. And if you take this as the derivative, the way it is, if you take that as d prime, then d prime will be 0 when that top part's 0. Why is that? Well, because, an expression that's a fraction, a over b is going to be 0 if a is 0, but b isn't 0. I mean, that's the way arithmetic works, right? What 0 divided by 7? It's 0, right? That top number's got to be 0, but the bottom number's got to not be 0. So in our case, if we take 10t minus 30 and set it equal to 0, that will be our critical number. That's what makes the derivative 0. And that's just 3, right? 30 minus 30 if t is 3. Okay, so t is 3. So that's kind of our answer. It'll be a little more complicated than that. But t is 3. That's the time when the objects will be closest. Okay, so remember there were 3 questions that I asked you to think about when I introduced this scenario. When will the objects be the closest? Oh, that's what we just found. That's time. That's at t is equal to 3 seconds, okay? And then I wanted to figure out where they'll be and how far apart they'll be. So let's talk about those next 2 things. And the way I'll do that is I thought, let's just give all those answers and then try to visualize it at the same time. If you don't like visualizing things, that's okay. Nobody's going to force you to try to imagine what it looks like. But here I did draw this to scale, and I did want you to see it. I thought it would be a nice thing to imagine now that we've solved the problem. But they start here, and then at t is equal to 1, they're here. They're getting a little closer. And at t is equal to 2, they're here. Still closer. And then at t is equal to 3, they're here. And then that right there, that line in green, that's as close as they're going to get. And as the time advances from there, they just get further apart. So it's like they move closer and then further apart. Okay. So yeah, when they're there, that's as close as they're going to get. And that's at t is equal to 3. So, all right. So here's a summary answer to all those questions I posed at the beginning of the video. They're closest at t is equal to 3. Where's object 1 and 2? Where are they? Well, we can go back to that original statement of the problem and figure it out. I mean, put 3 in here. Tell me if you move 2 seconds or 2 units to the left per second, where are you going to be at 3 seconds? You can put 3 in, right? You'll get -2 and 7. And here you'll get 0 and 3. Okay? So we could go back to these to figure out where they're going to be. So that first object will be at -2 and 7. The second one will be at 0 and 3. That's where they'll be. This is when they'll be closest. This is where they're each going to be. And then what's that minimum distance? How close do they get? Well, so we could, if you want to, use the distance formula right here to figure out how far apart they are at those points. That's one way to get this number, root 20, which is about 4.47 units apart. If you want to, we could do it other ways. This formula right here gives you the distance at any time. So if you want to know how close they are when t is 3, if you were to put 3 in for t right here, it would give you the distance apart. And you get root 20 that way too. So there's different ways you could go about that, right? But they all come from that first number we got when we solved the derivative being 0, okay? All right, so right there in this green bubble there in green ink, there's my answer to all 3 questions I wanted you to think about when I introduced this scenario. I would like to show you one more thing. You might find that as you continue to study math and things that use math, that there's always a lot of talk about curves. So let's say, what does the curve look like for this or that situation? So here in this problem, we might consider looking at the distance versus time curve. Okay, in other words, like here's this formula. It gives me the distance that these objects are away from each other at any time. It's a function of distance versus time. If you want to visualize that, you could plot a curve, let's say time on the horizontal axis, d for distance on the vertical. This, it turns out to be what that curve looks like. They start off at a distance of root 65, okay? It's a little more than 8 units apart, and that minimum distance as they approach each other and then drift further apart, that minimum distance occurs when t is 3 and it's root 20, right? Just like we found, but we could see that if we had a detailed image of the curve. There's the graph of this thing. It looks a lot like this. Now I just sketched this freehand, but that's in fact what it looks like. It's concave up and so on. It has a minimum point. And on it would summarize all of our findings that we had when we answered the question.